So last time we showed that the set of all computable problems was countable. That's what we kind of showed. We showed that because we know now that the set of all finite strings over some finite language is countable. And then because of that, we know that Turing machines are essentially finite descriptions of infinite sets. We noted that when we were making a universal Turing machine. And we used that to basically construct a description, a complete description of any Turing machine with a finite string over some fixed alphabet. And so because of that, we had that the set of all Turing machines kind of had this correspondence with finite strings over some fixed alphabet. And since we know that finite strings over some fixed alphabet is countable, it follows the set of Turing machines is countable. And since we define computability as is decided by a Turing machine, we now have the set of all computable problems is countable. So that's what we showed last time, i.e., remember, R denotes the set of all computable problems. Is the recursive set, is the recursive languages. This is omega. That's how we denote that. We also noted that all, this is the class of all languages, was equal to the power set of 0, 1, star. Right? We can without loss of generality just think of all decision problems as over the binary alphabet 0, 1. We know how to do that now. And what this essentially says is it's the collection of all subsets of finite strings, which is exactly what a language is. So anything in here, anything in here is a subset of 0, 1, star. That is, anything in here is a collection of finite binary strings, and that's precisely what we're defining as a decision problem. So this is the thing we need to investigate the cardinality of. This is what we need to do next. So we're going to have a discussion about the power set in general. I want to note a couple other things, though, first. Also, we showed that n to the k, the natural numbers to the k, which, by the way, is n cross dot 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 cross n, k times. We showed that this was countable for all k. And so another natural question related to cardinality is, what is the cardinality of n to the n? Where what I mean by n to the n is just keep going. It's just the product n cross n dot 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 with no end. So if you think about this guy here, n to the k, what essentially is this? It's ordered k tuples of numbers, but maybe a more simple way to think about it is it's just a finite sequence of numbers, right? If I have n to the 5, then that's ordered 5 tuples, but really that's just a sequence of 5 numbers. Whereas this guy right here, this then is infinite sequences of numbers. That's really what this is. So to begin with, let's think about the power set in general. So that's another natural question we're going to ask, and we're going to find the answer to that as we find the answer to the first question. To begin, let's investigate the power set operator in general. So we noted earlier that the power set for any finite set we noted that the cardinality of the power set of A always seemed to be 2 to the cardinality of A. Whoops. But I didn't justify why. So let's talk about why that is. And it's a lot easier to talk about why that is now than it would have been earlier. The reason it's like this now is, well, let's just kind of look at an example. Let's say A is equal to A, B, C, D, E. the reason that the power set of A, the reason that the power set of A has 32 things in it, 2 to the fifth, is because there's a natural bijection. There is a natural bijection between binary strings of length 5 and subsets of A. Let's kind of demonstrate that. What I can do is I can essentially do this. Where's my mouse? There it is. I can just kind of label these. So obviously this is a set of cardinality 5, and so there's a natural kind of bijection between the elements of this set and the natural numbers from 0 to 5, or maybe 1 to 5. So what I'll do is I'll kind of write that down. I'm going to identify A with the number 1. I'm going to identify B with the number 2, C with 3, D with 4, and E with 5. And then what I'm going to do here is I'm just going to look at the binary string x, let's say, equals 0, 1, 1, 0, 1. This essentially gives me a bunch of true or false statements about whether or not the first guy, whatever I've labeled as the first one, is in A. So basically what this says, this is going to correspond to B, C, E. Why? Basically what I'm looking at here is the nth bit tells me whether or not the nth element of A is in the set. Let me go ahead and say that. Idea: the nth bit of X tells me whether or not the nth element of A is in the set. And that's it. So another example would be if I looked at the string 0, 0, 0, 0, 0, that would obviously be the empty set. If I looked at the string 1, 1, 1, 1, 1, that would be the set A itself, and so forth. Every set has a binary string, and every binary string of length 5 has a set. And so there's the exact, so this is a natural bijection, and we know now that since bijection is our notion of sameness, then if two things have a bijection between them, then they are the same size. So since having a bijection gives us a measure of size in the first place. Well, let me kind of say, since having a bijection is our notion of size, of classes of size, it follows that, well, let me go ahead and say it, or write it down in math. It follows that the cardinality of the power set of A is equal to the cardinality of what? 0, 1 to the cardinality of A. Right, where this is basically what I mean by that is it's the set 0, 1 cross the set 0, 1 cross ... cross the set 0, 1, where there's 5 of these, or cardinality of A many of these. Right, where so a sequence, a finite sequence is just a tuple, right? You can always think of it that way. And so that's why. And so obviously we now know that also that if you have the product of two sets, then the cardinality is going to be the cardinality of the product. So this is equal to the cardinality of 0, 1 times the cardinality of 0, 1 times ... times the cardinality of 0, 1, and that's equal to, of course, 2 to the fifth, or 2 to the A. So that's true. So that's why. That's why the cardinality of the power set of a set is, of a finite set at least, is always the 2 to the original cardinality. Let's consider now, though, the power set of a countable set. Let's consider the power set of the natural numbers. There is just as obviously a bijection between subsets of natural numbers, or rather I should say subsets of a countable set, of any countable set. Right? I put n here, but I really could put any countable set that I wanted to. There's just as obviously a bijection between subsets of a countable set and infinite sequences of binary numbers, of infinite binary sequences. Right? I mean, if I just let, for n it's easy. Basically just say, the nth element of the sequence. So if I have 0, 1, 1, 0, 1, 1, 1, dot, 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 what I've really said here is that, this guy means that 1 is in the set, or I'll say this is 0. This guy right here means that 2 is in the set. This guy right here means that 4 is in the set, and 5, and 6, and so forth, right? The nth bit tells me whether the nth number. Or if I have any countable set here at all, I could do the same thing. I just do the numbering. I count it. I come up with my counting scheme, essentially. And then I basically look at a binary sequence as saying that the nth bit tells me whether or not the nth element is in the set, is in the subset. So I can always do this. There's always a natural association with countable sets and infinite binary strings. So in other words, the cardinality of the power set of n, just like above, is actually equal to the cardinality of 0, 1 to the n. And in fact, for any countably infinite set A, the cardinality of the power set of A is going to be equal to the cardinality of 0, 1, again, to the n. In particular, what is all? Let's go back up here. All is the power set of 0, 1 star. 0, 1 star is the set of all finite strings of zeros and ones. And we noted that the set of all finite strings over any alphabet is countable. In other words, the cardinality of this guy, well, we've identified exactly what we want to look at, or at least what I want to look at. In particular, all. Well, let me go ahead and say, in particular, 0, 1 star is countable. So the cardinality of all, the cardinality of the set of all languages is equal to precisely this. There is exactly as many decision problems as there are infinite binary strings. Now, before I actually prove that this thing is uncountable, let me relate one more thing to the story. I want to kind of fell all of this in one big swoop, so I'm going to kind of bring the conversation to one more specific guy. Right. So before showing that this guy is not countable, consider R. Not R, the set of recursive functions, but just the R that you're used to. R, the real numbers. The real numbers can also be associated with infinite binary strings. And I want to show you that. So there are many ways to identify real numbers with infinite binary strings. I'll show you that carefully. We'll do it kind of two different ways. One way is kind of not going to be a bijection. It'll be an injection. But the other one will be a bijection. But if I just wrote down the bijection, the bijection's a little hairy to look at. So So maybe the simplest way is to do this first. So have a real number x. Start by coding the digits in binary using 4-bit strings. So I'll say that so if I have the number, let's say x equals negative 8, 6, 8, 5, 4, 0.3268. And maybe it'll even go on. Maybe it has an infinite. Maybe it's like a non-terminating decimal point. So what I'll do is I'll do the standard kind of binary encoding of the digits. So I'll say, okay, 8. What is 8 in binary using 4 bits? It's 1, 0, 0, 0. 6, on the other hand, that's 0, 1, 1, 0. 3, that's 0, 0, 1, 1. 2, that's 0, 0, 1, 0. 5, that is 0, 1, 0, 1. And 4, that is 0, 1, 0, 0. And then what I can do with x here, I think you already kind of see where this is going. We need to be a little careful because the way I'll do it is I'll use the first bit to code whether the number is negative or positive. So basically this is going to associate with this following number. I'll say 1, and this bit here codes whether x is positive or negative. So if there's a 0 here, then x is positive. If there's a 1 here, then x is negative. So the 1 here codes the minus sign. And then 8, that's 1, 0, 0, 0. So that'll be 1, 0, 0, 0. That'll be the next 4 bits. And then the next 4 bits will code 6, so 0, 1, 1, 0. And then 1, 0, 0, 0 again. And then a 0, 1, 0, 1. And then maybe I'll have like a special code. I didn't realize this when I was doing this originally on my notes, but there'll need to be a special code for this guy, which is easy to do. I can kind of say that since I only need to go up to 9, that would be 1001. I'm not using the next number up. So let's just say this is 1111. That no digit needs this as its coding. So I'll just say 1111 codes that, and then so on. 3 ends up being 0011. Then you got to 2. That's 0010. Dot dot dot. And so you see that this is an injective function from the set of real numbers into the set of binary sequences of length of infinite binary sequences. Excuse me. It's injective in the sense that if I give you 2 unique binary sequences, I know that there's a single number that maps to each one. Or if there is a single number that maps to each one, then there is. Actually, I think this is pretty obviously a bijection. Is it? Yeah, any binary sequence I want codes a unique. Well, no, that's not necessarily the case. The more typical way that you define a bijection between the real numbers and the set of infinite binary sequences is this way. Given an infinite binary string, I'll write it like this way. I'll say x equals x1, x2, x3, x4, dot, dot, dot. So each of these is a bit. Each of these x values is either 0 or 1. The way I wrote it down, and I kind of wrote this haphazardly, just kind of thinking it out of my head, but you're not going to like this, but I'll explain it after I write it. Can define x, which maps to, sometimes you read this arrow thing here as maps to by the function. If I'm defining a function just kind of on the fly, I'm going to say f of x equals -1 to the x1. So the first bit, just like above, will say whether the number that I'm mapping it to is negative or positive. And then sum k equals 1 to infinity. So it's an infinite sum. So if you're not familiar with calculus 2, just kind of avert your eyes. X to the 2k. What I mean by that is I'm going to put the even. I'm going to do something here with the even digits. And then that's going to be times 2 to the k minus 1 plus x to the 2k, x sub 2k plus 1. So now I'm going to do something with the odd bits each time, and that'll be times 2 to the minus k. So this is kind of hard to look at. I couldn't find I didn't think too hard about finding a way to clean it up and make it look better. But the idea is simple enough. Basically what you're saying is, I'll just do an example. So for instance, 1, 0, 1, 1, 0. What's this going to map to? Well, it's going to map to a negative 1 times, actually I should put bars here. The negative 1 times everything. Negative 1 times what? It'll be 0. So 0 times 1 to the 0. That's right here. So k equals 1 here. That's going to be the first digit. X sub 2k, that's k equals 2. So that's x2. That's the second digit. It's 1 to the 0th power. Plus 1 times, that's going to be this guy. That's x sub 3 times 2 to the negative 1. Oh, whoops, that should be a 2. This guy here should be a 2. And then the next guy is 1 also, so it's 1 times 2 squared. And then the next one is 0 plus 0 times 2 to the negative 2. Wait, 2. Oh, wait, no, this is a 1, excuse me. 1. That's what that is, and then it stops there. Everything else is 0. You can also kind of say it's plus 0 times 2. I wrote 1, 0, 1, 1, 0, but really that's not a string. Really, the only infinite binary string is 1, 0, 0, 0, 0, dot, dot, dot. It's just trailing zeros. That's really what I meant when I wrote this number here. So I can't, this is not an infinite binary string. This is kind of what I was really trying to do. So the next one would be 0, and that's 0 times 2 to the 2 squared plus 0 times 2 to the negative 3 plus 0 times 2 cubed plus 0 times 2 to the negative 4 plus dot, dot, dot. But it's all 0. So if you kind of put this all together, you end up with negative 1/2 plus 2, and that's it. That's just equal to negative 2.5. So that's how that infinite string code. And then with a bit of calculus, so I'll just kind of say this. I'm not going to do the calculus here, but with a bit of calculus, or just an understanding of kind of like representations of numbers in general, with a bit of calculus, it can be seen that this is a bijection between the real numbers and the infinite binary strings. So because of that, we now have kind of a new piece of the puzzle. We've kind of got the whole thing framed that I wanted to have framed. So we started out looking at all, and this is a computability theory kind of series. So this is what I'm thinking about. But we've identified some things that we're really also investigating. By investigating the size of all, we're really investigating the cardinality of power sets of countable sets. I'll just say 0, 1 star is the placeholder, but it could be any countable set. We're also looking at the cardinality of the real numbers. We're also looking at the cardinality of infinite binary strings. These are all the same. So if I can figure out any of these, then I've got the answers to the rest of them. And also, we've also sort of got 3 different ways to think about decision problems at this point. So let me summarize that. So also, with all of these bijections defined, we can now think about decision problems as being many different things, kinds of things. Basically, what I mean by that is a decision problem can be thought of as, let's list them. So number 1, so a decision problem can be thought of as a set of finite binary strings. That's kind of the original conception of them. But they can also be thought of as a single infinite binary string. So I can think of a decision problem as an infinite set of finite binary strings, or I can think of it as a single infinite binary string, or even more crazy, I can think of it as a real number. Just a real number. Yeah, so any of these are valid, and all of them are useful. All of these ways to think about decision problems are useful. So it does pay off to think about decision problems in all of these different ways. So the next video is so important that I think I'm going to cut this one off. And in the next video, what we're going to prove is that that 0, 1 to the n is uncountable. An incredibly pivotal proof, not just to computability theory, but to mathematics in general, but especially to computability theory.